Thank you, Sarah. Hello, graph lovers. I'm very excited to be here today. I'm Salvatore Furnari. I am a big data engineer at Agile Lab, and I've worked with Neo4j for a major customer since 2022 as a full stack graph developer and system integrator. Among our activities, my team and I monitor database to prevent downtime and outages. In this journey, I'd like to share my journey. In this session, I'd like to share my journey on this project and the challenges that we have faced. So before I begin, I say just a few words on how Neo4j's memory works under the hood. We know that in the very end, Neo4j is a Java process, so it runs in a Java virtual machine. So we can see its memory. We can divide its memory into two areas. We have the off-heap memory and on-heap memory. The page cache in off-heap memory, we have the page cache, which contains indexes and cache declared data. And in on-heap memory, we have the instantiated Java objects, and the on-heap memory is handled as is handled by a garbage collector process as every Java process in the world. So let's zoom in a bit. We have the heap memory divided into two. We can further divide the on-heap memory into two areas. We have the new generation, where there are newly created objects, and old generation, in which there are objects that have survived for a sufficient period of time. So we know that each time a garbage collection runs, we have the JVM process is stopped, and then it is resumed when it has finished. So it's crucial that the garbage collection time lasts as little as possible. For we have different garbage collection cycles. We have a minor garbage collection cycle, which is responsible for reclaiming short-lived objects that are no longer used, and the major garbage collection process, or full garbage collection, which is the equivalent for the old generation. So let's see what happens when we have when the old generation memory is full. This trigger a long garbage collection process, which may take minutes. And during this period, the affected node is unavailable. Okay, so the cluster experiences a decreasing of performance. The network is the node doesn't communicate with the other nodes in the cluster, and for this reason, all the cluster loses the majority quorum. The writes are blocked. And there is more. When the affected node comes back online, that needs to synchronize its database with the others, and there is an increase of the traffic load and also of the disk operations that are very, very intensive. So we detected this kind of problem using Dynatrace, which is an end-to-end tool that provides end-to-end infrastructure observability. It tracks the memory usage for both old and new generation. Here I extracted these four charts from Dynatrace. We can see here how Dynatrace detects long garbage collection time. We have the heap memory. As observed, at a certain point of time, the memory spiked suddenly, and the new generation becomes full, triggering a minor garbage collection process that moved all the objects into the old generation memory that also filled up, and started a major garbage collection process that lasted minutes. So this is a very unpleasant situation. So we initiated a process to find the cause of this problem. of this frequent reboots and the high memory usage. Of course, the first step is to identify the queries uniquely. We have a very common architecture that consists users interact with the Neo4j through microservice deployed on a Kubernetes cluster. Okay, so we added a unique identifier which allows us to track uniquely the queries, and we can see what are the slowest queries and which microservices using them. Okay. Of course, in the second part, I'd like to show you how I optimize these queries. I don't have much time, so let's jump into the core. We have several ways to traverse the graph. This is a very crucial aspect because we are in a graph, right? So we have to extract data as fast as possible. We have to scan the graph as fast as possible. Neo4j offers several possibilities. We have quantified path pattern start from Neo4j 5.9, but this is not feasible for our context. So we used at the beginning we used the custom APOC, but this solution was not efficient, and comes with an higher cost of the maintainability. It's hard to keep aligned the custom APOC with the official plugin. So for this reason, this solution was not efficient. So I have developed a new plugin starting from scratch using the Neo4j traversal framework, and I developed a plugin and which is tailored to the domain's business logic requirements. Okay, so the new plugin is lighter, easier to maintain and to update. Another hint, very important, is to keep care when you use to be careful when you use aggregation operations such as collect. Okay, we are having memory issues, right? So when dealing with million of nodes and relationships, these operations, if it's possible, it's better to avoid these operations and return results to the microservice as a stream. In this way, the microservice can process data in a more efficient manner. So in the last part of this session, I'd like to give you some numbers. We have a water distribution network, okay, consisting of pipelines, reservoirs, water towers, and so on. Here, the network operator, the owner of the network, wants to extract the data. For example, we want to extract parts of the network at any level, at a specific direction. Okay, each element of the network is modeled as a node in the graph. We have several relationships that are self-explaining. Open pipe and closed pipe refer to a flow of water between the elements. So this is the first microservice. In the left, you can see the previous query. In the right, the new one. Here, there is what they call a hidden aggregation. You don't see the collect keyword, but there is still an hidden aggregation in the APOC plugin, which collects relationship and nodes. In the new plugin, I removed this. And I return a relationship as a stream. So I reduce the overall memory footprint of the query. So these results are extracted by JMeter. I started this. I used JMeter to extract these results. These are the 500 slowest calls And you can see the differences between the old query and the new query. We have a reduction of average by 64% and very similar to the maximum. Then also in this microservice, I removed the aggregation operation and also the unwind the double. There is a double collection operation, as you can see here. Much better to return these results in a stream and remove the necessary list compression. This statement is also deprecated starting from Neo4j 5. Here you can see the result of the time reduction. And then we have the last microservice that is one of the most used in our domain. We start, there are no, the two queries are more or less similar, but the difference is that in this with the new plugin, the query performs much better, as you can see in the results here. Okay, we have an average execution time decreased by 93%, and the maximum time decreased by 96%. So thanks for attending, and happy graphing.